Welcome. This is a very exciting week. So finally, we're going to prove Gödel's theorem. And what will be nice is that we've done so much already that actually it'll be very, very easy. So we're going to go slow, and it'll be nice. This is the version of the theorem that we'll be proving. And in a moment, I'll tell you about the more famous formulation of the theorem, which will in fact just be an easy corollary of that. So what we're going to show is that there is no Turing machine that's able to do the following. So it runs forever, and as it runs, what it does is it prints sentences. And the sentences it prints are sentences of the language of arithmetic. So things like that, and more complicated things. And it keeps going and printing things, and eventually, each arithmetical truth is going to get printed. So for example, that one is going to be printed eventually. And it's never going to happen that any arithmetical falsehood gets printed. So in other words, what the theorem says is that arithmetical truth is not Turing computable. And the way to think of that is that you can separate functions into two classes, those that are simple enough that you can come up with a finite computer program that can compute it, and those that are too complex for that. And it turns out that arithmetical truth is too complex for that. So arithmetical truth cannot be captured finitely. There is no way of writing down a finite list of instructions such that that captures all there is to arithmetical truth. And of course, arithmetical truth is baby mathematics. It's the simplest part of our enormous mathematical corpus. So what the theorem shows is that mathematical truth is incredibly complex. Now, the more famous corollary, which we'll talk about later, says that if you have a sufficiently interesting mathematical theory, then you can't axiomatize it in a way that's consistent and complete. And we'll see how once you prove that, then it's very easy to prove the corollary. Okay. So now I've talked about a Turing machine printing arithmetical truths and not printing arithmetical falsehoods. All of that presupposes some language. So if you're going to state an arithmetical truth or an arithmetical falsehood, you need some language with which to state it. So a lot of what's going to happen, a lot of what we're going to talk about is just we're going to get clear about what that language is. So we're going to consider a language which I'll call L, and which I'll just refer to as the language of arithmetic. And one sentence of L is going to be that one, but there will be others. Okay. So the crucial lemma that we need to prove, and unfortunately that's kind of boring to prove and long, is that language of arithmetic, that thing L, can be used to express certain uncomputable functions. And the reason we've done all the work already is because we've already given particular examples of functions that can be shown to be uncomputable, such as the halting function or the busy beaver function. So what that lemma means is that the same language that we use to express very simple things like these can in fact capture very, very complicated things. So here's what it means more precisely for the language to express a function. So take a function f of n that goes from natural numbers to natural numbers. So for example, it might be the halting function, such that if you give it a number, it gives you a 1 if the Turing machine corresponding to that number halts and a 0 otherwise. Or it might be the busy beaver function, such that if you give it a natural number, it gives you the productivity of the most productive Turing machine with that many states or less, and so forth. So take a function, and we're going to say that that function can be expressed in the language of arithmetic if in that language you can state a particular formula, and we'll talk more about what that is, such that the result of applying n and m as inputs to that formula is going to be true if and only if the result of applying the function to n is m. So in other words, what's going to happen is that we're going to be able to state in L, just like we state this, some weird formula, for example, halt. And here halt is just going to abbreviate, a long string that's going to include maybe pluses and times and quantifiers and weird things, such that that is going to be true just in case, or maybe I'll state it like that. That's going to be true just in case the nth Turing machine halts. And that's going to be true just in case it's not true that the nth Turing machine halts. Now, of course, this should now seem kind of weird, because on the face of it, when we do arithmetic, we're just talking about numbers and properties of natural numbers. So how can you have a language which is designed just to talk about natural numbers? How can you have it express things like halt? Well, that's what the lemma shows, and that's the long and boring construction. Okay. So what I'm going to do, yes?
But what does it mean, halt, in the language of arithmetics?
Good. So we're going to, that's a good question, which we're going to have to get to. So we'll get to that as we work through the lemma. Yeah, I'm glad you asked this question, because the answer should not at all be obvious at this point. Yeah.
It seems that arithmetic is computable. Like I can write a Turing machine that can, I give it like any string of arithmetic comprised of like pluses and minuses and times and stuff like that. And then it just prints out the answer of the formula I've given it. So if I can write out this halt formula, then why can't I just take that formula, give it to the Turing machine that is a calculator, which I have on my computer, and now I have the halting program?
You have just proved Gödel's theorem.
Great.
That's it. That's it. That's it. So I'm going to repeat what you just said a little bit more slowly. That's very cool. Here is a proof of Gödel's theorem that makes use of the lemma and makes use of what we've seen earlier, namely that things like the halting function or the busy beaver function are not computable. So I'll do it for the halting function. So suppose for reductio that the theorem is false. So suppose for reductio that there is a Turing machine that's able to do those things. Then let's use it as a subroutine for another Turing machine, which as usual will be our evil Turing machine. And what the evil machine does, maybe I'll write this down. So this is what the evil machine does. It takes k as input. And what it's going to do is it's going to use a Turing machine that does 1 through 3 as a subroutine to determine whether the kth Turing machine halts. So it takes k as input, and then it runs m, which m is just that machine that we're assuming exists, but that doesn't really exist. So it takes k as input. It runs m as a subroutine until it gets a formula of the form halt k and then something. And of course, that something is just going to be an answer to the halting problem. So what it does is it erases everything on the tape except for alpha, which is going to be a 0 or 1, and halts. So if that machine were to exist, we could construct a Turing machine that solves the halting function, or the busy beaver function. And we know that that cannot be done. I'm going to write an m here. So that is the proof. It's that easy. I really want everyone to be super clear about that, so I'm going to stop and basically let people think and hope for questions. And as usual, a question I would be delighted with is, like, could you just say that again? Or, like, I didn't understand, or whatever you want.
So then this thing would assume the contents of the lemma that the halting function is part of our arithmetic truths, right?
Exactly. Exactly. So that's right. So it's thanks to the lemma that we know that if we run m and wait long enough, then it'll eventually print a formula of the form halt. And that's how we know that the evil machine will terminate. If the lemma wasn't true, then we wouldn't be able to get that. There would be no guarantee of that. This is important, so I'm gonna say it once more, just because it really is crucial. So the plan for the evil machine is to run m. That is, it's to run a machine that does things 1 through 3 until it finds a certain formula, until it's printed out something of the form halt k and then either a 0 or a 1. So it's, of course, going to wait forever unless m really does print out a formula of that kind. But what the lemma says is that the language of arithmetic can express the halting function. So in other words, there is a formula of the right kind in the language of arithmetic. We still don't know what it looks like, so we're going to see what it looks like when we look at the lemma. But it really does exist. So the subroutine is going to eventually terminate. And this means that this evil machine really is going to compute the halting function. So one way of thinking about this proof is that it shows just how complex arithmetical truth is. So we saw that the halting function is too complex to be computed by a Turing machine. And we saw that the busy beaver function is too complex to be computed by a Turing machine. What this shows, I mean, assuming the lemma, is that the language of arithmetic can express all these functions and more. So arithmetical truth is at least as complex as any of the functions it's able to express. So it's super complex. So shall we move on to the lemma? All right. So the first thing I'm going to write down is going to make the lemma seem even more amazing. because what I'm going to do is I'm going to write a list of symbols on the board. And our language is going to be restricted to strings of those symbols. So anything that our language says has to be built out from things on this list. Okay, and here's my list. Okay, and I think that's it. Maybe I forgot something, but that's basically it. Yes? Oh, yes. I forgot something essential. Thank you. Oh, and variables, of course. OK. So I think now I've forgotten nothing. So let me go through the list and tell you what each of these things is. So the first thing is that each of these things is a symbol. So each of these things is going to be a component of our language, which is going to say something about the world of arithmetic. So that guy is a name for the number 0. That guy is a name for the number 1. That guy is a name for the operation of addition, multiplication, exponentiation, a name for the identity relation. That doesn't name anything. It's just left parenthesis, right parenthesis. That expresses negation, conjunction, and these are quantifiers. And I'm going to explain these in greater detail. So I don't think I even need to write what these mean because they're so familiar. But I'm going to write down what these are. OK. So what the lemma says is that using just these symbols with those meanings, you can express a formula that captures the halting function or the busy-beaver function. So let's start by getting some practice in the language. And I'll slowly explain what the guys on the right-hand side mean. OK. So first observation. Using just those symbols, you can build a name for every natural number. So the name for 0 is there, for 1, a name for 2, a name for 3, a name for 4, and so forth. So I'm just going to abbreviate those in the usual way. OK, so far so good. The next thing to note is that one can express simple identities. So one can say things like 2 plus 2 equals 4, 7 plus 3 equals 3 plus 7, 2 to the 2 equals 4, and so forth. OK, but in order for things to get interesting, we need to start bringing in those. Yes?
Why are the parentheses necessary?
So they're definitely not necessary here. I put them in just because philosophers are pedants, and I was taught to do these things by philosophers. They always put in the parentheses. But in this case, it's not needed. Of course, it really would be needed in a different case. So for example, we need to distinguish between those two.
And how do you make negative numbers?
No negative numbers, at least no negative numbers expressed directly. That's part of what's so amazing. I believe this really is baby arithmetic. I mean, one thing we'll see is that you can use numbers to code up ordered pairs of numbers. So if you wanted, you could use ordered pairs to code negative numbers. So in a sense, you can say all sorts of things, but it's just you can't say them directly. OK, so the negation symbol is the easiest of our weird symbols. So we can use that to say things like 2 plus 2 is not 4. Of course, that's false. But our language allows us to say not just true things, but also false things. So if you want to say that 2 plus 2 is not 4, then you just put a little negation symbol there. And conjunction is similarly simple. If you want to say that 2 plus 2 equals 4 and 4 equals 2 plus 2, then you can just say it like that. OK, so now let's talk about quantification. So the reason we need quantification is because otherwise you can't express any generality. So using the symbols we've talked about so far, you can, for example, say each of these. You can say 1 plus 2 equals 2 plus 1, and 1 plus 3 equals 3 plus 1, and so forth. But you can't say that in general 1 plus something equals that plus 1. So the way one says this is as follows. One says, for all x, and that 1 is just a label to distinguish between different variables. For every x, x plus 1 equals 1 plus x. And indeed, one can say something more general. One can say for every x1 and x2, and this illustrates why we need the different labels. So addition is commutative. So a good thing to have in mind is to try to wrap your head around what a variable means when it doesn't have a quantifier in front of it. So for example, what does that mean? So x plus 3 equals 17. What does that mean? I think that the best translation into English is this means something like it plus 3 equals 17. And then you say, who's it? And the answer is, well, I don't know. You haven't been told. The it really only makes sense when you add quantifier. And then that's the equivalent of saying something like everything, or every number, is such that it plus 3 is 17. Of course, in this case, it's something false. Yeah?
Is the only quantifier we're worried about for all, or do we care about there exists?
We do care about there exists. But what's nice is that there exists can be defined using symbols already on the list. So in fact, we can define exists using the universal quantifier and negation. Can anybody tell me how to do it? So in other words, what I want is I want to be able to say things like there exists something such that x plus 1 equals 7. There exists an such that x plus 1 equals 7. But I want to express the same idea using just symbols on that list. So can anyone tell me how to do it? And the hint is you're going to need to use negation and the universal quantifier.
So anytime you want to say there exists x such as 5x, that's equivalent to not for all x, not 5x.
Exactly. That's exactly right. So what this says is it's not true that every number doesn't have this property. It's not true that every number is such that if you add 1 to it, you don't get 7. And the only way for that to be true is for there to be some number such that if you add 1 to it, you get 7. And as he said, that's true in general. So generally speaking, that can just be defined as that. OK. Now, in a similar vein, suppose that instead of talking about conjunctions of sentences, we wanted to talk about disjunctions of sentences. So suppose we wanted to say that 2 plus 2 equals 4, or 2 plus 2 does not equal 4. So we want to say this. So how could one express that using only symbols on our list? And a hint is that you're going to use conjunction and negation. So what one can do is one can say, it's not the case so for this to be true is for either that to be true, or that to be true, or both. So in other words, what we're saying is, look, the world can be any way it wants as long as these guys are not both false. And that's what this says. It says, look, the world is not such that that one's false, because its negation is true, and that one's false, because its negation is true. So you can think in general of phi or psi as a definition for that. OK, so one last definition. One last definition. What about if-then? So suppose you want to say, if 2 times 3 equals x, then x equals 2 times 3. Yes?
I'm going back to the previous thing. I have a question. Why is a double negation necessary?
It's not. So double negations can always be eliminated. So it's generally going to be true that that is equivalent to that. So that was redundant. I just wrote it in to emphasize that the way I got from the first line to the second line was just by adding negations on both sides. But that's a good point. So how could I say this? How could I say that if 2 times 3 equals x, then x equals 2 times 3? Yes?
It's just the same as the previous one, except that you add a negation at the front.
So can you tell me how to?
So the previous one was A or B equals negation parentheses negation A. Sorry. So it's the same as the previous one, except that you just put a negation to the front, because A then B is the same as not A or B.
Is that what you mean? Good. Excellent. OK. So you can define if phi then psi as either of these, which are easily seen to be equivalent. So let's do it in terms of disjunction. So what this says is that for it to be the case that if phi then psi, then one of two things need to happen. It needs to either be the case that the antecedent doesn't hold, or it needs to be the case that the consequent does hold. In other words, the only thing that's not allowed is for the antecedent to hold without the consequent. Yes, Damien.
Probably worth mentioning that the natural language if-then it's controversial, but it's very probably not exactly equivalent to that if-then. But this is close enough to what we mean to be able to be used in mathematics.
That's right. So Damien's absolutely right. So basically, this only works when you're dealing with mathematical truths, which are, for example, necessary. But things can easily go wrong if you try to formalize the natural language if-then using this method. OK. So now we have all our basic building blocks, and we can start having fun with the language. So suppose we wanted to do this. Suppose we wanted our language L to be able to talk about pairs of natural numbers. How could we use these symbols to somehow talk about pairs of natural numbers? Because that's going to be the crucial thing we're going to need. So here's a cool coding trick one could use. In fact, we've used it before. So suppose we wanted to talk about the pair AB, where A and B are natural numbers. Oh, you have a suggestion?
Can you say like, can you note that as like the product of like the 8th prime number and the bth prime number?
Yes, that is something you can definitely do. But that presupposes an ability to talk about the 8th prime number and the bth prime number. Now, here is a fact which is not obvious, but it's true. That's actually not so easy to say in this language. So, I mean, you can certainly name them all. But if I told you, define a function f such that when I give you k, it outputs the kth prime, that's not so easy. In fact, the way to do it is to first start talking about primes and then like build your way up to those kinds of things. Now, there is an idea very close to the one you gave, which does work. So let me describe that one. So suppose you wanted to code up this. Then one thing you could do is you could look at this number. Of course, in the official language, you don't ever raise the type. But I'm raising it here because that's what we're used to. So you can take A and B, and you can use them as exponents, the first one for 2, the second one for 3. I've added these ones just in case one of these happens to be 0, so that doesn't trivialize the resulting number. The reason this is a nice coding system is because suppose that I give you a natural number, and I say, I'm using this coding scheme to code up a pair. You would be able to recover the pair, because the number I gave you would have been of this form. And what you do is you just factor it and find the exponent and recover A comma B. So we have a coding scheme that allows us to code pairs of natural numbers as natural numbers. So then the question of how to get L to talk about pairs is this question. Is the question whether you could define a new formula pair which is such that this is going to be true just in case x1 codes using this system a pair whose first component is x2 and whose second component is x3. So one at a time, I encourage you to do this on your own. It'll be fun and easy, and it'll be helpful for Wednesday.